Good morning, good afternoon, good evening to all of you. We have a lot to cover today, so I would like to start the KiboCUBE Academy online session. Okay, hold on, let me change my screen here. Okay, before we begin, just some housekeeping rules. First of all, if you have any questions, please use the Q&A box to ask them. Please do not write it in the chat. It will only be delivered to the host and panelists, but we want the questions and answers to be open to all of you. So please make sure to write them in the Q&A. And second of all, please answer our questionnaire, the feedback form that we will be putting in the chat box later on. So my colleague Wenben will be actually active in the chat. So he will be providing you with useful links through the chat box. And one of them would be the URL link to our questionnaire. So please make sure to answer that. We would really like to hear your feedback on the KiboCUBE Academy sessions and really want to learn your opinions about it. And last but not least, if you are on social media, please use the hashtag access to space for all, KiboCUBE and KiboCUBE Academy to help us promote this session. We are active on Twitter, Facebook, LinkedIn, and Instagram. So with this, today's agenda looks like this. First, we will be going on to the CubeSat technologies part by Dr. Toshinori Kuwahara. After that, we will be doing the CubeSat launch and operation part by Dr. Yuji Sakamoto. And after that, we will have a Q&A session. So if you have any questions, you don't have to wait until the Q&A session. Keep putting them in the Q&A box and we will be answering them. But also, we will make sure to address them at the very end as well. Before we go into the KiboCUBE Academy session itself, I just want to introduce the KiboCUBE Academy and the schedule because we have a lot of things coming up this year. So all of you probably know what KiboCUBE Academy is, but it is an online educational series that JAXA, UNOOSA, and with the support of UNISEC have been doing from 2021. And it is really an educational content that provides theoretical knowledge to develop, operate, and utilize small satellites. So it really covers the whole life cycle of small satellite development. And as you can see on the right-hand side, we have a wonderful series of pre-recorded lectures on our website. You can have a look at them now. You can find the PDF document itself and the video on our YouTube. So if you have any specific interest in any of the topics covered there, jump to our KiboCUBE Academy page, and then you will get to see the presentation and the recording is there. But also for this year, we have some online sessions coming up. So you're in one of them right now. Thank you for joining today. And then we have 3 more actually coming up. So one is on Sunday, the 1st of October. This is actually not online, it's on-site in Baku. So this year, the IAC, the International Astronautical Congress, will be held in Baku in Azerbaijan. So we will be doing an on-site event for KiboCUBE Academy there. In the middle of October, we will be doing another online session. And the topic will be really to give you final tips on building a strong application for KiboCUBE, which is open right now, which I will mention a bit later on. And then in parallel, we are planning to do some technical consultation sessions for you online. We will release the details and open calls in July or maybe August. It will be on our website, so please keep checking it. But we will have a lot of things going on for KiboCUBE Academy, so I just wanted to mention that here. Also, I also want to mention about KiboCUBE. So as I said, the actual opportunity to deploy your 1U CubeSat from KiboCUBE is open for applications. So how to find the documents is you go to the Access to Space for All website. So basically you go to UNOOSA, Access to Space for All, and then you click on the satellite development track, and then you will find KiboCUBE under that. And basically, when you go to the KiboCUBE index page, you have to scroll down a bit and then go to the rounds page. And this is where you will find all the documentation you would need to apply to KiboCUBE. And basically there we will ask you to read all of the documents very carefully. You have all the information there. And I will say it is a lot of information. So please read them carefully. And of course, join the upcoming KiboCUBE Academy live sessions. As I mentioned earlier, we will be giving you tips on how to really fill in the application form, but also some technical tips that you would need to understand when you apply to KiboCUBE. So make sure to join the live sessions. And of course, watch the on-demand pre-recorded KiboCUBE Academy webinars that I just mentioned. So as you saw on the list, we cover the whole range of satellite development. So please have a look at those webinars. It would definitely be helpful for you. And yeah, last but not least, please submit the KiboCUBE document on time. The deadline is the 31st of December, so you actually have plenty of time to go through all of these documents and fill in your application form. Maybe I'll just introduce the schedule as well. So beginning from July, the announcement of opportunity opened on the 2nd. And now you're here in July where we have the KiboCUBE Academy live session. And as I've mentioned earlier, we have a few webinars coming up. I just want to flag one more, which is not KiboCUBE Academy itself, but it's a KiboCUBE related webinar. In September, in mid-September, it's the regulatory webinar. So when you apply for KiboCUBE, we will be asking you to be in line with international guidelines. For example, the ITU guidelines for frequency allocation. And of course, when you launch the object, you will need to register that through the UN. So we will be explaining about those regulatory parts. And also we have other guidelines such as the space debris mitigation guidelines, the long-term sustainability guidelines, and we will be touching upon those guidelines as well. So if you're interested in that side of KiboCUBE, please make sure to join this webinar in mid-September. The details will be finalized hopefully soon in the next coming weeks so that we will be able to give you the exact time and date. And after that, we have the KiboCUBE sessions, and you will need to submit by the 31st of December. After that, the schedule is as you can see here, and it's explained very clearly in the document, so please have a look. But yeah, for this round, we are targeting the deployment to be sometime in 2026. So it is a long but exciting journey, and we really hope that this KiboCUBE Academy session today will actually help you take the first step. So with this, I'd like to go move on to the sessions now. So I'd like to invite to the floor Dr. Toshinori Kuwahara, who is the Associate Professor at the Department of Aerospace Engineering at Tohoku University.
Okay, thank you very much. So once again, hello everyone. So thank you very much for attending this KiboCUBE Academy live session. So I'm very honored to be here today to give you the lectures. So I hope you enjoy the lectures. So this lecture is a live session online lecture number 11, Introduction to CubeSat Technologies. So again, my name is Toshinori Kuwahara, Associate Professor at the Department of Aerospace Engineering of Tohoku University, Japan, and also the Chairperson of UNISEC Japan. So my research topics are space development, utilization, and exploration by small spacecraft technologies. So now let's start the lecture. Okay, so here is an overview of this presentation. So I will start with an introduction to space systems, followed by introduction to CubeSat systems, definition of satellite systems, CubeSat payload systems, and finally I conclude my presentation. So this lecture is basically based on the on-demand pre-recorded lecture number 1 and number 7. So chapter 1, the first chapter is the introduction to space systems in general. So on this slide, I'd like to introduce the major satellite application fields. So there are a wide range of satellite applications which we can benefit from. So the first category is the Earth observation. So these include meteorological observation, oceanographical, geographical, coastal area, atmospheric observation, and disaster monitoring and prevention, and so forth. Some of them are illustrated in these beautiful pictures on the right side. So the second category is communication. Satellite broadcasting, telephone, internet, etc., as you might know, belong to this category. The third category is navigation. So these are global navigation satellite system and traffic management system, such as air, land, water, railroad, etc. The final category on this slide is, last but not least, the science applications. So starting from the astronautical observation, microgravity experiments, such as medicines, pharmacy, etc., and space explorations such as moon, asteroids, planets, and deep space explorations belong to this category. So first of all, we need to understand about satellite orbits when we talk about space technology utilizations. There are many different types of satellite orbits, so I'd like to introduce them. So here I have illustrated several typical satellites orbit in this figure. The blue one, first of all, is the geosynchronous orbit. It's also called GEO. The orbit altitude is about 36,000 kilometers. So geostationary satellites are located on this orbit, and they are rotating around the Earth once a day with the same rotational velocity of the Earth. So when you look up, these satellites seem to be at the same position in the sky throughout the day, generally speaking. The green one here is the sun-synchronous orbit, also known as SSO. So an SSO is a kind of a polar orbit and flies over the north and south pole regions. So together with the effect of the Earth's rotation, satellites in SSO have a chance to fly over most of the places on the Earth. So moreover, the sun direction relative to this SSO is constant throughout the year. So you have the same illumination condition on the observing Earth's surface. Therefore, this orbit is suitable for Earth observation. The last one, the red orbit, is the ISS orbit. This one. The orbit is tilted with an inclination angle of about 51.6 degrees. The altitude is about 400 kilometers. But because the orbit altitude is relatively low, the ISS orbit also belongs to low Earth orbit, or also known as LEO. So satellites released from the ISS will also follow a similar orbit as the ISS. So unlike the SSO, the sun illumination condition of the ISS orbit changes with the time. So you need to consider several important effects on your satellites, such as power generation and thermal control. So as indicated here, the most appropriate orbit for the mission needs to be selected. On the other hand, other words, your mission needs to be designed according to the available satellite orbits. So practically speaking, if you utilize the satellite release opportunity from the ISS, your satellite needs to be designed in a way that it can survive in the ISS orbit for a long time period. So for the satellite operation, you need to understand the characteristics of satellite orbital motion. So I'll explain these one by one on this slide. So satellites in ISS orbit rotate around the Earth about 16 times per day, which means that one revolution of the orbit takes about 1.5 hours or 90 minutes. So Earth also rotates once per day. As a result, the relative velocity between the ground station and the satellite is on the order of about 7.7 kilometers per second. The satellite operator has a limited amount of time for communicating with the satellite, which is about 10 minutes or less per contact, and you have several contacts a day. So this also depends on the geographical position of the ground station, of your ground station. The satellite operator sends commands to satellites from the ground station and receives telemetry data from them, in most of the cases via radio frequency communication. For satellite operations, the following aspects must be considered. So as listed here, so satellite orbit and mission lifetime, communication system, ground station, link budget design, operational phase, and regulations, and so on. So satellites orbiting in high inclination orbits can cover a large portion of geographical area on Earth. So here I have an animation of a satellite on the ISS orbit and its ground track. So you can now understand how the satellite can cover a portion of Earth due to the combinational effects of satellite orbital motion and Earth's rotational motion. This feature of global accessibility can be utilized for Earth observation. So you can conduct the periodic, frequent observation of ground area under your spacecraft. And communication, you can have communication contact with ground stations in the visible area underneath your spacecraft. environmental measurement. So you can measure the space environment, such as magnetic field radiations for a wide region, etc. So higher orbits can have a wider field of view, and lower orbits can facilitate higher ground resolutions of Earth observation. So satellites are basically continuously falling toward the Earth. So this free fall microgravity environment can be also utilized for experiments related to material science, bioscience, medicine, etc. The space also provides unique environments such as vacuum, high radiation, strong ultraviolet light, cold and hot temperature, and existence of atomic oxygen and plasma, etc. So if you think about space utilization, you can consider these important characteristics of the space environment and space systems. So let's examine the ISS orbit in more detail. These are the parameters here of the ISS orbit. The orbit altitude is about 400 kilometers. The inclination is about 51.6 degrees. The orbital period is about 91 minutes. So it is also very important to know that the orbital altitude of the ISS is changing by about plus or minus 20 kilometers due to the effects of atmospheric drag. The higher the initial orbital altitude of your spacecraft at deployment, the longer the mission lifetime you will have. So as I already mentioned, the CubeSat deployed from the ISS stay in almost the same orbit as the ISS. So slight differences in initial relative velocity and different mechanical characteristics such as mass and shape, and hence ballistic coefficient, make the CubeSat separate from each other into different orbits. So this is the 3D view, and this is the ground track view of the 2D ground track view of the on the world map. So as you can see here, the ISS orbit covers the ground surface of regions with relatively lower latitude, between 51 plus and minus 51.6 degrees. So ISS rotates around the Earth about 16 times a day, while the Earth rotates about 22.5 degrees during one orbital period of the ISS. So this offset in this direction is about 22.5 degrees. Okay, then the next chapter, the chapter 2, is about introduction to CubeSat systems. So on this slide, I am showing the comparison between the traditional large satellite and the new small satellites. So this is a large satellite of JAXA, and these are exemplary small satellites. And this is me. So let's take a look at these key parameters: the mass of the satellites, the cost, and the development time. So compared to larger satellites, small satellites are characterized by having small mass, low development cost, and short development time. So in addition, larger satellites need dedicated launch vehicles. And because they are very expensive, they are required to be highly reliable and cannot assume a lot of risk. And also, though the performance is very high, the frequency of observation of large satellite is low because you cannot launch several large satellites due to the cost issues. So on the other hand, thanks to the characteristics of small satellites, there are several key benefits, as summarized on the right side. So first of all, the small mass means frequent launch opportunities. So you can launch many of them by a single launch, and you can also launch them as a piggyback satellites together with the main large satellite. Secondly, because of the low cost, you can try challenging missions. And also you can establish large constellations and networks of small satellites, which could provide very frequent observations. Thirdly, because of the short development time, you can utilize brand new technologies. So thanks to these features, small satellites are regarded as suitable platforms for space education, as well as rapid new technology demonstrations. This slide illustrates the mass categories of small satellites. The smallest category is the picosatellite here, which is ranging up to about 1 kilogram. The next largest category is the nanosatellite, ranging up to about 10 kilograms. The third category is the microsatellite, ranging up to 100 kilograms. Then the last category in this slide is the small medium satellite, ranging up to about 1,000 kilograms. But when you talk about CubeSats, their mass category is now ranging from pico to microsatellites, as illustrated with this red line. So, and they are becoming bigger and bigger. So I have already shown you several pictures of CubeSats. So one new CubeSat is a 10 centimeter cube with mass of up to about 1.33 kilograms. So some standards are available, and I have listed them up here. So the first one I introduced is the CubeSat Design Specification Revision 13, the original one, organized by the California Polytechnic State University. So it is publicly available and this link. So this standard provides a basic idea of CubeSat. So I recommend that you are informed about it as the first step. These are several more working documents. There are several more working documents available in the community. So the second one I introduced today is the CubeSat system interface definition organized by the UNISEC Europe. This standard suggests interface definitions for the internal electrical components of CubeSat. So this is available here. So the third one is the ISO standard. A standard for space systems about CubeSat is established in 2017, which addresses CubeSat deployer, and related verification of assurance and quality terms and metrics. The fourth one is the GEM Payload Accommodation Handbook, Vol 8D, so released by JAXA. I think this is the most important and relevant document for you when you apply for a launch opportunity through KiboCUBE Academy. So our GEM stands for Japanese Experiment Module, which is another name of the Kibo module. So both English and Japanese versions of Revision D is available here. So though a 1U CubeSat is a 10 centimeter cube, the dimension in the rail direction is a bit longer than 10 centimeter, as illustrated in this figure, just for your information. So on this slide, I have summarized the CubeSat deployment opportunities from the Kibo. So Kibo provides options of JSOT in 3 different forms: 3U, 6U, long 6U, and wide 6U. So consequently, there are these kinds of form factors of CubeSat which you can utilize for your own project. So they are 1U, 1.5U, 2U, 3U, 4U, 5U, as well as long and wide 6U. So it's possible that your satellite is stored into the pod together with satellites developed by other project teams. So among the possible form factors of CubeSats, the 1U CubeSat is especially the best platform to learn essential engineering skills and technologies for satellite development and operation at the first step. So these pictures below illustrate the outer appearance and inner components of a 1U CubeSat, exemplary one. So a 1U CubeSat is the simplest implementation, and the larger CubeSats, larger CubeSats can be utilized depending on the technology level and mission requirements. So a smaller format is mainly for fundamental functionalities, and larger formats are required for missions which require larger sensors, accurate attitude control, and a large amount of data transfer, etc. Though the form factor is very small, CubeSat components are getting more and more sophisticated, and nowadays there are a lot of commercial CubeSat components available in the market. So these are some of the sample commercially available components here in this picture. With the help of these commercial products, you can construct some components by yourself, and you can buy the remaining components from the market. And in this way, you can now start using CubeSats very seamlessly from scratch, and can gradually develop your own technologies step by step. Now we came to the chapter 3. So in the following chapter, the definition of satellite subsystems, I'd like to explain about the general functional classification of satellite components, together with the examples of CubeSat devices. So first of all, the functionalities of a satellite system can be classified into several subsystems, which are closely related with each other. This slide tries to illustrate the relationship. So this is the typical classification into subsystems. So they are the power control system here, communication system, command and data handling system, structure and mechanism system, thermal control system, attitude control system, orbit control system, and payload system here. The attitude control system is sometimes also referred as the attitude determination and control system, as it needs to determine the satellite attitude first in order to control it. The attitude control system and orbital control system here are sometimes treated as a single subsystem as attitude and orbit control system. So, as illustrated, I have put the payload system in the middle here on the top of all the subsystems. So I wanted to emphasize that the payload is representing your satellite mission objectives, and all the subsystems exist to fulfill the required functionalities to achieve the mission objectives with the payload. Also, all subsystems except the payload system are denoted as the satellite bus system, with the payload being the passenger among the other subsystems of the bus. So in addition to this, I point out that you also need to pay attention to the harness system of the satellite. Harness system. The harness system is, in other words, the electrical cables to connect components. So harness systems are usually regarded as a part of the power control system or command and data handling system. The reason that I put this extra here is that the harness cables inside a CubeSat have a great influence on the satellite assembly. So I will show you some pictures in the following slides. In CubeSat projects, it has more importance than bigger satellite projects that you carefully design the harness system and plan their routing inside the very limited envelope of the CubeSats. Though all the subsystems are equally important, I will try to explain from the most essential ones, in my opinion. The first subsystem I pick up today in this sense is the power control system. A power control system manages power generation by solar panels, a storage into secondary rechargeable batteries, and distribution of power to the satellite components. So this combination of components I mentioned, the solar cells, batteries, and the power control computer here, can be regarded as the power control system. The power control computer is usually referred to as the power control unit or power control and distribution unit. So sometimes the power control unit and power distribution unit can be separate components. So PCU and or PCDU sometimes convert the supply voltage to the satellite components inside. So power control system shall be highly reliable as compared to other onboard components. So if your power control system is functioning very well, then you can try to repair other failed components by conducting power cycling. That is, you power off the failed device and then power on the device again and see if it recovers. So I think you sometimes encounter similar situations with your laptop computer, personal computer. So what do you do in such a situation? So you reboot your computer, right? So we do the same in space too. To ensure this capability, the power control system of your satellite cannot fail in the orbit. The size of solar cells and capacity of the battery shall be determined based on the power consumption requirements of the satellite mission. These are the pictures of exemplary power control system components: solar cells, batteries, and some power control units. Sometimes the power control system is closely integrated with the communication system, as it is convenient for you if you have more remote control on the power control computer via radio wave communication. The device in this picture here is such an example of an integrated component. Here I have an example of a power control system. So this is a 2U CubeSat RICO developed by Tohoku University. So this satellite is the world first CubeSat released from the ISS. So this table summarizes the specification of the power generation, power storage, and power consumption of the CubeSat. The power generation of this satellite was on average about 3.2 watt without the solar panel deployment and 4.7 watt after the panel deployment. You can imagine that the order of available power for your satellite too, from this example. The power consumption was about 4.9 watts at the maximum during the communication, in this case. The power consumption in the standby mode is kept sufficiently low so that the generated power can be charged to the battery to survive the eclipse during the Earth's shadow and to allow a higher power consumption when required. The next subsystem I pick up is the communication system. As the satellite operates remotely in space, information exchange through communication are indispensable to make the mission of the satellite meaningful. The communication throughput, namely the amount of data you can transfer, especially for the downlink in general, determines or limits the entire performance of the satellite system itself. For high-speed communication, a higher electrical power is required, and the temperature of the transmitter increases during the communication. And please remember that typically a ground contact lasts about 10 minutes or less. The receiver shall be ideally powered on at all times so that the satellite doesn't miss any commands sent from the ground station. The transmitter can be turned on and off according to the ground contact schedule. This is important to save electrical power for the satellite. The picture below illustrates an exemplary S-band radio frequency transmitter and receiver, also showing the outer and inner appearance of an X-band transmitter. the amount of mission data downlink can be increased by using more than one ground station if available. So collaborative satellite operation is therefore very useful. The communication system also require an onboard antenna. So low frequency radio waves, that is longer wavelengths radio waves, require a larger antenna. VHF and UHF frequency bands are widely used for CubeSats, and they require an antenna with larger dimensions. So high frequency bands such as S-band and X-bands, which are also used for high-speed communication for CubeSats, require a smaller antenna. It is often the case that a Yagi type antenna is used for the low frequency band, and dish type antennas are used for high frequency bands for the ground station, as illustrated in this figure. So the next subsystem is the command and data handling system. The command and data handling system, often denoted as C&DH, it manages data handling components, commanding, monitoring, data storage, signal processing for communication, and error handling inside the satellite. So certain levels of autonomous functions need to be implemented in C&DH so that satellites can survive in the space environment. A high level of reliability is required for the C&DH components too. When the computer fails to function correctly due to, for example, radiation effects, the power control system shall power cycle the computer. The power cycling is power off and then power on, either autonomously or by telecommand sent from the ground station. There are many different kinds of onboard computers. So this figure illustrates an onboard computer I use for a 1U CubeSat. So this computer is very simple computer based on PIC. On the other hand, this picture shows examples of two commercially available onboard computers with high computational capabilities and large onboard memory storage and digital signal processing. So onboard computers define the capability of the onboard data handling, and you need to design or select appropriate ones for your purposes. The next subsystem is the structure and mechanism system. So let's take a look at the structure first. The satellite structure systems are the main interface with the launch vehicle. So in the case of CubeSats, the rails are the contact points between the satellite and the pod. The outer dimensions, surface area and surface treatment of the rails and outer envelope of the entire satellites are specified. The structure systems shall withstand the launch environment such as vibration, static acceleration, shock, acoustic, air venting, pressure, etc. So this picture shows the structure system of a 1U CubeSat as an example. So mechanical system include separation switches, deployable antennas, deployable solar panels, shutters, booms, and any other mechanically moving structure elements on the satellite. Mechanical systems shall be safely stored during the launch to ensure the secure release of the CubeSat from the pod. This picture shows a solar panel deployment mechanism as an example. The next subsystem is the thermal control system. The thermal control of a satellite can be achieved in two different ways, the passive control and active control. As active control needs electrical power, such as heaters or coolers in general, a passive control is the usual thermal control concept of CubeSats. Passive thermal control utilizes different surface materials with different thermal optical characteristics in order to adjust the heat exchange among the satellite, deep space, and the Earth. An aluminum surface contributes to warming up the temperature, and a Kapton tape surface contributes to cooling down the thermal condition, for example. Here I'm showing an example of the 1U CubeSat Freedom we developed. So Freedom actually doesn't have solar panels and only has a battery system. And Freedom introduced passive thermal control with a tape material pasted on the satellite surface for a certain portion to keep the satellite temperature low enough. The principle of thermal control is the same for larger CubeSats. You need to run a simulation analysis and design your satellite thermal properties appropriately. The next subsystem is the actual control system. Actual control capability is required depending on the mission operation of the satellite, such as pointing observation. Pointing the observation instruments toward the target, and pointing high gain antenna toward the ground station for high-speed communication, as illustrated in this figure, and orienting solar panels toward the sun for larger power generation, and so on. For the attitude control, attitude determination is also necessary beforehand, and therefore attitude determination sensors and attitude control actuators are required in general. So there are also two types of attitude control: passive control and active control. And there are many different kinds of attitude control modes. So detamperring control is one of them. And there are several pointing control, such as inertial pointing, area pointing, target pointing, velocity direction pointing, etc. Then the last subsystem is the payload system. So payload systems are the onboard components dedicated to the satellite's missions. The good practice is to define clear interfaces, the mechanical interface and electrical interface, with the bus system. In this slide, you can see the examples of CubeSat, 3U CubeSat S-Cube. This picture is showing the payload module of the CubeSat. So 1U is assigned for the payload instruments, and about 2U is assigned for the satellite bus system in this example. Finally, I will show you the harness cables of the CubeSat. So this is an example of the 3U CubeSat S-Cube. So I hope you can get the sense of how important and critical careful design of the harness system is, and that you assign enough envelope for them from the very beginning of the satellite development. So this concludes the explanation of the satellite subsystems. So now we come to the next topic, CubeSat payload systems. So each CubeSat has its own missions. So the larger the CubeSat is, the more payload instruments can be carried, and the more advanced the missions are that can be conducted. Examples of CubeSat payload instruments include observation cameras, in situ space environment measurement sensors, a meta measurement sensors, communication instruments, and engineering demonstrations such as deployment mechanisms, advanced technologies such as new sensors, electrodynamic tether, etc. Today, I'd like to introduce you to 5 of these examples in the following slides. So this is an example of an Earth observation camera system. So this is the 2U CubeSat Raiko again. So it was implemented with an Earth observation camera system, as well as a new sensor, a star tracker, for the satellite attitude determination. So again, you can see that the harness system is very complex and takes a certain volume inside the satellite. So this is the first example of payloads. The next example is the meteor observation instrument. This is the 3U CubeSat SQ. It was implemented with a meteor observation camera system, and a gravity gradient boom was used to point the meteor observation camera toward the Earth's atmosphere for detecting incandescent meteors as they enter the atmosphere. It also had deployable solar panels. This is the second example. The next example is the signal measurement instruments. So recently, receiving and analyzing ground-based AIS, the automatic identification system signals from space, is attracting interest. So in this case, the receiver and the deployable directional antenna system are the payload, as illustrated here. So in this example, a 3-axis attitude control is utilized to point the antenna toward the Earth for detecting the AIS signals sent from ships, enabling tracking the positions of the ships with a higher geographical resolution. And the next example is the orbit demonstration of a thin film deployment mechanism. This example is the 1U CubeSat Freedom again. The payload was the deorbit sail for fast deorbiting and re-entry into Earth's atmosphere from the ISS orbit. The CubeSat had no communication system or solar cells. So this is the CubeSat Freedom, and this is the deployed thin film during the ground verification. Freedom demonstrated on-orbit deployment of the thin film based deorbit sail, which can be utilized for space debris mitigation and prevention using atmospheric drag. So this successfully demonstrated the orbit sail device is now available for CubeSats and micro satellites in the market. The CubeSat Freedom deorbited into the Earth's atmosphere in about 22 days after the release from the ISS, which is, we believe, the shortest record for the re-entry from the ISS orbit. The last example is the electrodynamic tether. So this is the 3U CubeSat Air EDT. The payload is an electrodynamic tether for the orbiting and re-entry into Earth's atmosphere. A 3-axis attitude control is used to control the satellite attitude during the extension of the electrodynamic tether. The device will be useful for space debris mitigation and prevention in higher altitude orbits, as it can operate independent of atmospheric drag. So I hope you now have a deeper understanding and clearer ideas of what you can achieve by means of CubeSats. So now I'd like to conclude my presentation today. So in summary, the characteristics of satellite technologies and CubeSat systems are described, and available CubeSat standards are introduced. The functionalities of each satellite subsystem, including the payload system, are described in detail. And some examples of CubeSat payload devices are provided together with real satellite projects. With this, I'd like to finish my lecture today. So thank you very much for your attention. Thank you.
Thank you very much, Dr. Kuwahara, for the very detailed presentation and lecture. I know this is a lot of information for you, but as my colleague Wenbin has shared in the chat, this is already on our website. Please download it and have a look again. And of course, this webinar is being recorded, so you will be able to review this after the webinar, and I will try to put up the recordings as soon as possible. So yeah, thank you very much, Dr. Kuwahara, and we will invite you back at the Q&A at the end.
Thank you.
Okay. Now I'd like to invite to the floor Dr. Yuji Sakamoto, who is the Associate Professor at the Division of Mechanical and Aerospace Engineering at Hokkaido University.
So my name is Yuji Sakamoto from Hokkaido University, Japan. So just a moment. I want to hide this one. Okay, my topic is CubeSat launch and operation. Hi. This is my introduction. So I was working at Tohoku University with Professor Kuwahara more than 15 years. And now I'm working at Hokkaido University in Japan. So I developed several micro and nano satellites so far. The first one was the SprySat. This is the 50 centimeter class microsatellite. The second one is already introduced in last presentation. This is RICO 2-unit CubeSat. And the third one is 50 centimeter class satellite. Again, this is Rising 2. And fourth one is this is Filipino microsatellite, Diwata 1. And the fifth one is this is Diwata 2, the second Filipino microsatellite. So my research topics are design, assembly, and evaluation of micro and nano satellites, and also satellite operations and ground station management. This is my topic. I want to start from a virtual tour, operation rooms introduction at first. Then I proceeded to the introduction to satellite operations and orbit and mission lifetime and the communication system, ground station, launch and first contact, and the mission operations, and the second video. Okay, I want to switch to the video. So this video is 5 minutes, 40 seconds. So I think this is a good intermediate break of our presentation. Okay, please watch relaxed feeling. This moment. I think that this Zoom bar should be hidden. Okay, this is the room, laboratory room in Tohoku University. This is a mock-up of our microsatellite RISAT. The mission was remote sensing by many new scientific payloads. So actually there is a remote operation center in this room. Also, there is a clean booth to develop microsatellite. Yes, this is a remote operation computers. Now it is turned off. Okay, we go out and walk in the campus. The city is Sendai in Japan. It's called the city of forest. So there are a lot of green forest. I think it is very beautiful environment. So now we are in the operation room. So for our first satellite, we were using this room to develop assembly the satellite. So now it's only dedicated to the operation. This moment. I'm talking something. I want to mute the video. So there is a power amp for the command transmit. This is the amp, low noise amplifier for the telemetry signals. Okay, I don't know the speaker. So this is showing the now direction of antennas, the -28 azimuth and 83 elevation. So the 0 azimuth means the north direction, and 180 degree is the south direction. So sorry, I'm not good at to keep cleaning. So there are a lot of computers and wires. So we are waiting the next satellite. It comes in 7 minutes from now. It is showing the 7 minutes to AOS. So AOS means the arrival of satellite. So now the most of hardware is turned off, except for the computers. 5 minutes before the satellite arrived, the lot of equipment is automatically turned on. So left one is controlling the ground station antenna direction. The right one is controlling the command transmitter equipment. This is command modulator, and this is the power amp for the S command uplink. And behind the wires, there is a motor DC supplier. This is the telemetry receiver. This is the computers. A lot of computers. Some computers are being used for the control of ground station, and some computers are being used for the satellite operations. Satellite operation means the communication with the satellite, not ground station. So now it is starting to control the antenna direction. So azimuth and elevation is being changed. I think this antenna is very old. It was, I think, 30 years. This moment, this is showing the receiving signal status. So now, before the arrival, and the every lamps are turned off. Okay, now already satellite comes. So now 2 minutes to maximum elevation, and the signals are already received. The left one is carrier signal, so it means the RF signal is high. And okay, we watch the antenna itself. It is now moving and tracking the satellite. I think it is just before the maximum elevation. So this elevation angle is possibly very high, 70 degrees. I'm not sure that this mouse cursor is displayed in Zoom, but yes, the tip of antenna, there is a box. So inside the box, that several antennas are included. So this ground station has the S-band telemetry and antenna, and S-band command antenna, and X-band receiving antenna. And also behind the dish, there is a Yagi antenna. This is to transmit the UHF signals to satellite. Yes, I'm pointing now. It is a Yagi antenna for UHF command. And yes, I'm pointing the box, antenna box. So there are several patch type antennas inside the box. Yes, this is the time shift. Just before the LOS, the loss of signals. Possibly now satellite is around the horizon. And this is the about 0 degree elevation. Now it's returned to the home position. Okay, the video is finished. This moment. So I return to the original presentation. This moment. I want to move that Zoom bar. Okay, okay, I return to the first topic, the introduction to satellite operations. I think some slides are same or similar to the last presentation. So partially I skip my talk. Okay, what do you need to think about for the operation of your satellite? Okay, this is actual real photo taken from the International Space Station. We call it ISS. Now two CubeSats. Okay, I changed the pointer. Where's the pointer? Yes, now around here, you can see the two CubeSats. One is the 1U CubeSat. The second one is the 2U. CubeSat. So please consider what you need to think about for the operation of your satellites. So the satellite rotates around the Earth about 14 to 16 times per day in low Earth orbit, and about 10 to 12 minutes per contact from a single ground station. And we can catch the signals 4 times per day. And the data communication time will be the total 40 to 48 minutes in total per day. So the satellite, we call the satellite operation. It means the send commands to satellite from ground station and receive telemetry from satellite. So this is the function of the communication. And also we need to think what kind of scenarios are prepared and to be set the satellite. And in visible time, the satellite will carry out some tasks. So it is included in the operation plan. Yes, I wrote here. So, okay, that's second page. So satellites cannot be repaired in orbit after the launch, of course. And we can only communicate with them to conduct the planned missions. And sometimes we need to solve unexpected problems or troubles. So variations of operation scenarios and procedures need to be considered and tested before the completion of satellite development. This is strongly related to software concept and design. So I emphasize operations are not the matter of only communication. This is relating to other subsystems, including command and data handling, attitude determination and control, power system management, and thermal design. Okay, section 2, satellite orbit and mission lifetime. Yes, this is the same figure in last presentation. So for micro and nano satellite developers, low Earth orbit LEO, this one, sorry, this one and this one. So they are normally selected because there are many launch opportunities. A short distance to Earth has some merit. So communication transmitting power can be decreased, and high resolution images can be obtained by a small telescope or camera. And satellites are released from the International Space Station. It has a 400-kilometer height, this one, and inclination is the 51.6 degrees. So in last presentation, there was a video, and you see that around the North Pole and the South Pole, the satellite in this orbit cannot pass. Okay, so this is just the same thing. So regions around the Arctic and Antarctica cannot be observed from the satellite in ISS orbit. This includes the northern regions of Sweden and Norway. Actually, we have another ground station in Sweden, so north part of Sweden. So from that ground station, the ISS small satellites cannot be observed. Also, the solar angle to orbit is changing every day. So this affects the daily observation timing to our specific location, specific ground station. It means that sometimes the satellite comes only sunshine, only daytime, and sometimes it comes only nighttime. So it's not stable, the arrival time. For ISS-related satellites, all sunshine phase, this is the full sun phase, in other terms. So continues for a few days around the summer and winter. So solar angle to orbit can be more than 70 degrees, right figure, 70 degrees. So left figure shows the 0-degree case. And generally we call it, this angle is beta angle, beta solar angle. So, and this 0-degree case is the cold case. Cold case means that your satellite temperature will achieve minimum degree. And in hot case, so every time the sun shines and no eclipse phase. So it means that the satellite temperature can be converged to the very higher temperature. Yes, in cold case, it is 0 degrees Celsius, and it can be increased to 40 or 50 degrees in hot case. So you need to think about, don't forget about this phenomena. And this is explanation about the satellite lifetime deployed from ISS. So the lifetime is strongly related to atmospheric drag. In lower than 400 kilometer height orbit, atmospheric density is much higher compared to 500 or 600 kilometer height. The height of CubeSat can be decreased by atmospheric drag because the drag force acts in the backward direction, Generally, a 1U CubeSat can re-enter into the upper atmosphere with less than 1 year of orbital life. One example is 2-unit CubeSat. This was deployed in 2012, already 10 years ago, and the weight was 2.7 kilograms. So this year, actually, the atmosphere drag was stronger than usual, and the total lifetime was, this is the kilometer, this is the month. It was finished in 10 months. And the right figure shows the case of Diwata-1 Filipino microsatellite. It has 52 kilograms, but it was deployed from the ISS. So around 2016, the solar condition was very weak. Solar activity was very weak. So it can survive around the 4 years. So I think it was very good observation was achieved by the satellite. Okay, the topic is communication system. So in this section, I'll show the introduction to the communication system. So communication system is required for uploading commands from a ground station to a satellite and for downloading housekeeping and mission data, such as Earth images taken by satellite cameras. I think that, yes, the first available frequencies of VHF around 144 megahertz and UHF 435 megahertz. So they are in the range of amateur radio bands. And the satellite must have missions for public amateur radio users and public students, not only the engineering missions. Okay, also we are using S-band and X-band for the micro and nano satellites. The S-band is around 2 gigahertz and X-band is around 8 gigahertz. So they required some license and yes, ITU application in other ones. Okay, this is the world's first CubeSat Psi-4 and from the University of Tokyo. This has folding antennas that are deployed in space. So lower frequency bands require longer antennas. And the merit in these signals is in reasonable prices for the setup of amateur radio ground stations. This makes these frequencies popular with many CubeSat developers. But the merit is the slow data speed, such as 1 kbps or 10 kbps, etc. The one reason for the speed limit is the limited assigned bandwidth. It is very squeezed and a lot of users are using the signals. And also that these forwarded antennas must be automatically deployed just after the release from ISS. It is a problem. So when the antennas are not opened, the satellite cannot receive any command signals and cannot send any telemetry data. So any mission cannot be executed. And this failure, I think it often happens, especially for the beginner developers. This is the S-band and X-band. So they will be used for high-speed data communication. Example, 2 megabps by S-band and 20 megabps by X-band can be available. And wide assigned bandwidths can be used, especially for the X-band. So the merit is the ground station cost. As I show you in the video, the large parabol antenna system is required. And but the merit is the no deployable mechanism required. So low risk of communication failure, especially in the initial phase. So these are the patch antennas we originally developed, and it is assembly in the satellite with other antenna covers like this one. Okay, the high gain antennas require pointing control to satellite or pointing control to ground station in the satellite side. So narrow beam wires can achieve higher gain compared to that Yagi antennas. But especially for the satellite, power resource is required for both transmission amp and to the attitude control components. So in the operation, for S-band, it is not required the attitude control in satellite side, but for X-band, so the satellite must be controlled actively. Okay, to decide the specs of the communication system in design phase, we need to understand the analysis method of link budget. Acceptable data rates such as 10 kilobps, 100 kilobps, 1 megabps, etc. can be calculated by the balance of hardware specs. This technique is explained in a lot of reference books, and this is not a matter only for satellite design. I think it's general fundamentals for the RF communication. So it's not difficult to find a good book. But firstly, we need to decide the required hardware specs for both the satellite and the ground station. And the data modulation type will change the acceptable noise levels. So the famous modulation type is the FSK, EPSK, QPSK, etc. Communication distance is very important and will have a strong impact on deciding the data rate. So this distance is maximum when the satellite is around the horizon and the elevation is very low, around 0 degrees. And when the satellite is maximum elevation and the distance is shortest, and the RF signals can be stronger than this position. Okay, for topic is the ground station. Sorry, I want to check the time. Okay, yes, it's a very similar picture in the last presentation. The ground station antenna must be controlled to point towards the satellite during the observation chance. So both for the Yagi antenna type and this dish antenna type. So this Yagi antenna has a bit wider beam widths. I think it has more than 10 degrees, but this dish type, I think it is the 3 or 4 degree for the S-band, and for X-band, it is less than 1 degree. So a precise control is necessary for the dish antenna. And the satellite orbits, yes, the future satellite position and antenna direction can be calculated. So this is not difficult. And satellite orbits at a specific time are available in the 2 line element. This is open orbital information, and we can get from the public website. So I can say that every space objects are being surveyed by a United States organization, and yes, every satellite position can be calculated, everyone. So this is this figure shows a satellite position, and the ground station location around Japan. So this circle of the satellite indicates the visible area from the satellite. A ground station must be included in the circle of this circle. The best way is to prepare ground stations around the world. to increase the amount of mission data. For amateur radio satellites, every country can be accepted for the communication. But for remote sensing or other experimental communications, they are only allowed to communicate with specific countries, and it is defined in ID applications. Okay, the operation software is also important to establish an automatic control system. This is satellite operation software, and this is the, I can say, a very simple controller for the ground station equipment, this one. And also this is the control software for the every ground station hardware. So this one and this one is prepared by university, and this is the simple interface is the manufacturers. So I can say you will be very exhausted if you don't have an automatic system. So this antenna control software, so this one, is developed by university, including automatic control of the manufacturer simple software. After the completion of automation, I can say we don't need to care about the antenna control. We can concentrate on the satellite operation. Operators can concentrate on the data communication with satellites during the observation chances after the automatic ground station control. So telemetry data is distributed from the receiver, but I can say it is very bare and raw data, only hex data. So we need to convert them to the satellite status, decimal values, and the converted values, and also the image data by individual conversion models. So this kind of satellite operation software will be prepared for each satellite. And also the important thing, this must be prepared in electrical test phase of satellite. So some team will prepare after the delivery of satellite, then prepare this kind of operation software. It is the nonsense. So we need to develop the satellite itself, also our own the ground station software before the completion of satellite. Okay, we proceed the 5 launch and first contact. So I talk about the case when we use the service of ISS Kibo satellite deployment service. The satellite should be delivered to JAXA several months before the launch. And CubeSats are assembled into the JSSOD. I think that several types are already released. I can say this is very old type, and this can contain the maximum 3 unit CubeSat. So 1 unit, 3 PCs, or 3 new CubeSat, only 1 PC can be contained. And after the handover ceremony, this is ceremony, and JSSOD, including CubeSats, are shipped to the launch site for further integration to the cargo spacecraft. Yeah, I'll skip this one. So the cargo spacecraft, the HTV from Japan, is launched by was launched by H2B from Tanegashima Space Center. So the launcher will be changed in next launch. The cargo or spacecraft Cygnus is also available, often available. This is launched from the United States. So I think the delivery timing is longer. I mean, yes, for the Cygnus, we need to prepare the 3 or 4 months before the launch. So HTV approaches and docks to the ISS after a few days. And that container and the CubeSats are handled into the ISS. CubeSat experiences mechanical vibration during this launch. So the power supply must be turned off at all time until the deployment to space. CubeSats are prepared for deployment by astronauts. So JSSOD and the deployment pallet are transferred to outside. This is a pallet, sorry. And this is the satellite container. So you can see, yes, the side of the satellite. So they are attached to the tip of the robotic arm on keyboard, and then the astronaut triggers the switch for the deployment. So I can say your satellite can be touched by astronauts directly in space. So we need to be careful to remove the sharp edge or the fragile item, something, especially the face of this, the smaller shape, smaller side. Okay, this is the memorial photo. Just a moment. Sorry. Yes. So this is the Filipino microsatellite, Diwata 1. And this is a real photograph taken from the ISS. It was 2016. Okay, after the deployment ceremony, we need to come back to the ground station to catch the first signals. So most CubeSats automatically start their functions in space, including the RF transmission. We observe the first signals from satellites at our ground station. I think this is the most exciting moment, so they are very exciting. And I think the satellite health is checked, including especially the power generation, power consumption, and the battery charge and discharge state, and the temperature of the battery in initial pass. So this is the right goal to your CubeSat, and the left one is the actual photograph taken by Raiko, and the right one is also. So we need to confirm the successful command uplink as well as telemetry receiving at first. So a lot of CubeSat had defects in command function. Be careful of the electrical noise environment inside of satellite. So this is very important. We send the commands of camera trigger, for example, and to download the data and check the first light images. So this is the first light images. Okay, section 6, the mission operations. Okay, just a moment. This is appearance of our daily operation. So the appearance is a bit different from the previous video. So this was a different room, the old remote operation center. So actually, yes, I show you the ground station operation room, but the generally, yes, it is the 8-minute walk from the ground station site and our laboratory. So we set up the remote ground station inside the same campus. Okay, this is appearance of our daily operations. We use the satellite control software and we upload the prepared commands, then monitor the status and the downloaded image data. So these are the full image data. And yes, there is a Japan here. This is a fisheye camera, and this is the telescope images. And also we can check the thumbnail image, quickly check the thumbnail image. Then we download the full size image. So I show you the functions of satellite control software. In most satellite operations, you will make an original software for status decoding and quick sending commands. The status window is showing the solar power generation, including voltage, current, and watts, and the power consumption by the bus components. And the battery, there are 2 batteries. So battery voltage, current, and temperature is important. And also the on-off state of each primary components. And yes, there are red lamps to show the alert and the emergency values. So now they are all green in the normal states. Okay, actually, I don't recommend using only real-time commands. Real-time means that, yes, push the button and execute the task something. So it is a real-time operation. So I introduced the stored command function. The stored command means that, yes, the several commands, so they are not executed in real time, and they are just stored in onboard RAM, onboard memory, and it will start after the trigger or the time. So this is an example of the stored command definition. The first one is the camera on at specific date here, and the wait 5 seconds. Then attitude control to target, and we wait 3 minutes. 180 seconds. Then a camera take a photo and wait 5 seconds, and the camera is turned off. So this is the example of the camera observation. So by changing only the first line, this specific data is changed, then we can reuse the command procedure. So we prepare some scenarios, and the first line has only specific date, and the other lines only have the interval waiting seconds. So this is our typical stored command concept. Okay. So if we want to increase the precision of attitude control, I need to check the time, 9:30. We need to survey a flight data and compare them with simulation results. Then update their parameters, such as sensor alignment. This is showing the simulation result of the gas. Gas means the magnetic sensor, and it has three axis values. And the lower one is the flight data, the actual value, including the bit noise. So by adjusting the coordinates or the sensitivity or the offset, bias offset, then we can match of these two lines. It is important. Also, we often mistake the definition of plus and the minus sign. So this is really often it happens. And I can say we cannot avoid completely them. So we need to prepare to change the plus and minus, or the multiply 0.9, 0.8 or something. So this kind of adjusting commands must be prepared. Otherwise, we cannot control the satellite by this kind of very easy mistakes. And this is the operation routine. Firstly, yes, we make operation plan. This is a kind of text file I explained. We will create a new procedure or just assemble the previous procedures by adjusting the first line in specific time. We need to analyze the orbit and estimate the suitable timing of future tasks, execution timings. I think this work will consume an enormous amount of time, and the mission planner will be very exhausted. I experienced, and my students are also experienced. After finishing command preparation, the upload task, I can say it is a very routine work and simple. So it can finish 20 or 30 minutes. So after the completion of upload, this must be manned operation. This should be manned operation. But other tasks can be automatic operation. So yes, in daytime operation, we can check the telemetry or mission data. And also the nighttime, the ground station can work automatically. And that receiver, so receiving software is also executed automatically, and we can sleep good well. So before the completion of this automatic operation, so we were very exhausted, really. So I think that this kind of automatic, the method is very important. Yes, that's the conclusion, but I have 8 minutes more. So I prepared one more video. This moment, I want to skip a second one. Okay, this is that moment. I move this bar. Yes, 2 minutes and 30 seconds. So he is now, I think, waiting the satellite. It has not arrived. Yes. Now, yes, the 3 minutes to the arrival time, and he's changing the something, the modes of the receiver. And also, yes, this is the operation software. We push stored command, and load something file. Sorry, I hide the actual contents. Yes, it was included in the software, and it is decoded to the hex codes. Now, yes, I skipped something. Already the satellite comes. So yes, I skipped. Now 3 minutes to maximum elevation. I'm watching the left below. And yes, the data is now coming. You can see the pink bar is moving and some time is changing. And also, yes, I'm not sure what he is doing now. Yes. He pushed the stored command right button, and now the stored command, a lot of command frames are being sent to the satellite automatically. And now it is finished 26%. Yes, the movie is skipped. Now 100% finished. And he pushed SC start button. This is large button around the middle. So SC start button is the real-time command. So now, yes, it is executed in satellite side. That now it is being executed possibly. So in this operation, he uploads the scenarios and start the command, then just waiting, just watching the progress. What they are talking. Yes, battery is a bit warm, around 30 degrees Celsius. Okay, this is the example of the satellite operation. Sorry, I hide a lot of things. Okay, I moved back to the original presentation. Okay, yes, possibly it is a very good time. So now this is a conclusion of my presentation. Just a moment, I moved the bar. So CubeSat deployed, released from the ISS, will follow similar orbits as the ISS. And the orbit has different illumination condition of the sun throughout the year. There's a pointer, right? Mission duration of a CubeSat depends on the mechanical characteristics, and such as mass and the size and the magnitude of solar activity. This is the environment, and it is seasonally changing. So, and the link budget between the CubeSat and the ground station shall be carefully designed for steady communication in both directions, the uplink and downlink. And the important thing is the noise condition inside of satellite must be carefully surveyed and decreased as much as possible in the assembly phase. So a lot of CubeSats ended in failure by command link malfunction. And through mission planning, ground evaluation, stepwise observation, orbit verification, and efficient operation framework are important in the other research topics. Okay, this is the conclusion of my presentation. Thank you very much.
Okay, with this, I would really like to thank both professors for their very detailed presentations. As I've mentioned earlier, their presentations are online already. So please download them and have a good look again. And of course, this webinar is recorded again, and I will try to put it up as soon as possible so that you can review the recordings, share it with your friends and colleagues so that they can have another look as well. With this, I'd like to thank everyone for engaging with us with the many questions. As I've mentioned earlier, we will have more KiboCUBE Academy webinars coming up during the year. So yeah, we really hope that you will keep coming and attending these KiboCUBE Academy sessions, and we would really like to hear your feedback as well. So please answer the feedback form, the questionnaire form before you leave. And with this, we all wish you luck for KiboCUBE. If you're applying, and even if you're not, we wish you luck in the development of your CubeSats. And yeah, we'll see you in another session of KiboCUBE Academy. Thank you, everyone. Have a nice day. Bye.